So I'll be speaking on quantum recommendation systems, and this is joint work with Jordanis Kerenidis. So I'm going to take a rather classical perspective for this talk. So let's introduce the recommendations problem. So we have a preference matrix which is indexed by users and products. So think of M users and N products, and think of M and N to be very large. And we have some information about how much these users value these products. So the entry Pij is the value of item j for user I. And not all entries of this matrix are known. Most of the entries are actually unknown. And the samples from this preference matrix arrive in an online manner when the user expresses his preference for the product. So given this partial preference matrix, a recommendation system is supposed to find good recommendations for a particular user, say for U3. So in this case, U3, the good recommendations are the green boxes, which are labeled 0.8 and 0.9. And the recommendation system should find me something unknown, which is also likely to be rated high by this particular user. So in general, this task is impossible, but it is done in practice using the assumption that P has a good rank K approximation. So this is justified both empirically and also from a perspective that there are only a few factors that count in how much a user likes a particular product, and they may be weighed differently. So let's look at how classical algorithms solve the recommendation problem, and how taking a slightly different approach can give you a quantum algorithm with an exponential speedup. So the classical approach to recommendations is to perform matrix reconstruction. That is, you want to reconstruct the unknown entries of this preference matrix. So there are two popular approaches for this. The first one is to say that the unknown entries are 0, do an SVD, and then reconstruct the matrix using the low rank approximation. And the other is to do some kind of alternating minimization where you assume that this matrix P can be factorized as U times V transpose, where U and V are low rank. And then you fix U and try to optimize over V, and conversely. And after many rounds of this iteration, you reconstruct the entire matrix. So all these classical reconstruction-based approaches, we can store the SVD, the low-rank part of these reconstructions. But even with this pre-computation, when I actually want to make recommendations for a particular user, I will need time poly n. Because I need to reconstruct this vector of preferences for this particular user. It's an n-dimensional vector. So we reconstruct. So the classical algorithm would reconstruct this entire vector and choose the highest elements out of it. So to provide a recommendation classically, even with pre-computation, one needs order n time. And think of M and N to be large, so it's not possible to store the entire reconstructed matrix. Like, it would be prohibitive to do so. So one idea one could naively suggest is that how about sampling the important entries of the matrix? Like, a user comes into the system, and we sample the good recommendations for this user. And this would not require a reconstruction of this matrix and should be much faster. But classically, there are no such algorithms for matrix sampling. The best algorithms, it's almost as hard as matrix reconstruction. So the main idea here is that one can use quantum algorithms to perform this matrix sampling and come up with a much faster recommendation system in this sense. So the main result is that there is a quantum recommendation algorithm that runs in time poly k, polylog mn. And this is an exponential speedup over the classical reconstruction-based algorithms. So this rank parameter k is typically asymptotically much smaller than m and n. So let's look at a bit more detail in what the computational model is and what kind of speed up algorithm is achieving. So as in the classical system, we assume that the samples from P arrive in an online manner when the user enters the system, and they are stored in a data structure with polylog mn update time. And the quantum algorithm has oracle access to this data structure. So by this we mean this is the standard assumption in quantum computing, which is the same as used by standard algorithms like Grover search and so on. So the assumption is that this data structure in which the preference matrix is stored is accessible to the quantum computer via this oracle model, which is a reasonable assumption. So the setting is that the users arrive into the system in an online manner, and the system provides recommendations in time poly-k, polylog mn. And the guarantees and the sample complexity for the recommendation system are very similar to that for classical recommendation systems. So in this sense, the classical reconstruction-based recommendation system would require poly n time to make recommendations. And here we need only poly-k, polylog mn time. So this is a natural problem for which you do have an exponential quantum speedup. So the main tool is a quantum analog of singular value estimation. So let me quickly recall singular value estimation. So for a matrix A, one can write the singular value decomposition as A equal to sigma I ui vi transpose, where ui and vi are orthogonal vectors, and sigma I is a positive. And the rank k approximation AK truncates this decomposition up to k terms and optimizes this Frobenius norm. So in the quantum setting, we work with vector states. Like we have to encode these vectors into quantum states. And the encoding used is to have the vector entries in the coefficients. So we define this vector state ket x as summation I xi I. And for all unit vectors, one has a vector state. So the central algorithmic idea here is quantum singular value estimation. So there is a quantum algorithm with running time polylog mn over epsilon that given a vector state is able to estimate the singular values in a coherent manner. Like given alpha I ket vi, it is able to append and estimate sigma I bar, where sigma I bar is with an additive error epsilon of the Frobenius norm with high probability. So this is like a quantum analog of the classical SVD, and this is the main tool that we use to construct this recommendation system. So I'm not going to tell you about this algorithm, but I'll tell you how to create the recommendation system using this as a black box. So now let's look at the model. How do we construct a recommendation system based on matrix sampling? So the first step is to replace this preference matrix by a 0-1 matrix. So let T be a 0-1 matrix, which we define as Tij is equal to 1 if the item j is a good recommendation for user I, and 0 otherwise. And note that this choice of T is flexible. For example, you could say that Tij is equal to 1 if the preference is higher than the threshold, or it could be the best 100 products for this particular user, and so on. So for example, for the preference matrix earlier, here's the T. But the fact is that you do not have T. Like the system has a subsample of T. So T is not a known matrix. Instead, we have a subsample T hat, which is the information the system has seen so far. And the job is to construct recommendations from the subsampled matrix. So if we had T, then exact samples from T would be the good recommendations. And we want to, and instead we have T hat, and we want to reconstruct it using this T hat. So first, let's see. If we want to approximate T, then we do get good recommendations. For example, if you had an approximation T tilde, which was epsilon close to T in the Frobenius norm, then then because T is a 0-1 matrix, one would get good recommendations with high probability. So if we sample from T tilde, the probability of getting a bad recommendation is at most 4 epsilon squared. And this can be extended to a guarantee for typical users. So by typical users, we mean those who like the number of products. The number of products they like is close to the average, which is 1 plus gamma close to the average. So the low rank approximation, the low rank assumption on the recommendation systems translates to T minus Tk being less than epsilon T Frobenius for small k. And so you see that if I was able to sample from Tk itself, then I would have good recommendations. So we need to reconstruct, so we need to extend this to the subsampled matrix T hat. So the quantum algorithm would not produce an exact projection, but there would be some error in this projection. So it would be projecting to some singular values greater than sigma and some in a small range, 1 minus kappa sigma and sigma. So let's see what the subsampling framework says here. So we use the uniform subsampling framework first proposed by Akliopoulos and McSherry in the year 2001. So here the subsampled matrix, so with probability P, we are subsampling and rescaling the matrix. So A hat ij is Aij by P and 0 otherwise. And under this condition, we have a theorem which says that that if we look at this sigma k, we look at the approximate projection, not the exact one, then it's as good as the exact one, as A minus AK. So this theorem will be used. So we can set the parameters in this theorem so that T minus T hat is at most 9 epsilon TF. So in effect, this is saying that it's enough to sample from T hat sigma k. And the quantum algorithm provides good recommendations for most typical users. So let's now describe what the quantum algorithm is, and it's actually quite simple. So we start, so we recall that this ket x denotes the vector state corresponding to the unit vector x. And so we prepare the vector state corresponding to the row for user I, which is available to us. And then we project this down to threshold sigma, which is chosen to be 1 over square root k times a constant. And we obtain this approximate projected state. And then the algorithm is very simple. We just measure this projected state in the computational basis to get a good recommendation. And as I argued in the last few slides, for most typical users, the expected running time would be poly k poly log mn, and with high probability, the output would be a good recommendation. So I'm not going to discuss the quantum algorithm as we are short on time. So I'll just say how to do the projection, assuming the singular value decomposition is available. So let A have a certain singular value decomposition, and let's say we can prepare a certain vector state. So we estimate the singular values, sigma I bar with additive error kappa sigma over 2. And then we simply measure if this estimate is bigger than 1 minus kappa over 2 by sigma and so on. And it's easy to see that this does give the approximate projection to all singular values, singular vectors greater than sigma, and some in the range of error permitted by kappa. So basically, this gives us a natural problem for which there is an exponential quantum speedup, and leaves open the questions of whether one can obtain a classical recommendation algorithm based on matrix sampling, which has similar running time, or to prove a lower bound that would rule out such an algorithm, and to find more quantum machine learning algorithms with speedups over classical. Okay, thank you.
Since we're running a little short on time, maybe let's take questions offline and thank all the speakers again.